We will see expression for crippling load or critical load when both the ends of the column are fixed. Okay, so the last class we have seen when both ends are hinged, and the second one was one end fixed, other end free. Now, when both the ends are fixed, so what would be the critical load or crippling load formula, Euler's formula? Okay. So this is the figure. The figure shows where the both ends of the column are fixed. Okay, and it is subjected to an axial compressive load P, and length of the column is L. You could see here at the fixed end, it is subjected to a moment M naught. Okay, M naught at top and bottom end of the column. We are considering some section XX at a distance X from the bottom end. At the considered section, let Y be the lateral deflection. Now we are trying to write down the bending moment expression. So bending moment at the section is M naught is clockwise. With respect to this point, I'm taking moment M naught, so plus. So the sign convention for this type of bending is minus negative bending moment. So minus P into Y, P into Y. So we know that the bending moment is from solid mechanics, EI d square Y by dx square. So EI d square Y by dx square is equal to M naught minus P into Y. Okay, so d square Y by dx, so just rearrange it, divided by EI. We get the equation like this: d square Y by dx square plus P by EI into Y is equal to M naught by EI. So when the right hand side term is 0, the general solution, we know that Y is equal to C1 cos of root X root of P by EI plus C2 sine of X root of P by EI when the right hand side term is 0. Where if any right hand side term is, if you have any right hand side term, I mean term in the right hand side, you multiply it by EI by P, and whatever term left out on the right hand side, you just add it with the general solution. Now if I multiply with EI by P, the left out term is M naught by P, you just add it with the general solution. That becomes the final general solution for the above differential equation. Okay, so this is the expression for Y, that's a deflection. Since you have got a fixed end also, it should be differentiated with respect to X to get the slope equation. So after differentiating it, you get this equation or expression for dy by dx. Now applying the boundary conditions, let us determine the constants C1 and C2, which is nothing but the constant of integration. So this is what Y equation. This is dy by dx equation. At A, that is at the bottom end, X is equal to 0, deflection is also 0, slope is also 0, as A is the fixed end. Okay. Now let us substitute this with the above two expressions. Okay. At B, X is equal to L, Y is 0, and dy by dx also 0, because again, B is also the fixed end. Okay. So if you substitute in the equation, the first equation, top equation, C2 sine of 0 is 0. So cos 0 is 1 and Y is 0. So C1 you will get minus M naught by P from the deflection equation. Then again from this slope equation, X is 0, sine 0 is 0 and cos 0 is 1. So C2 dy by dx is 0. So 0 is equal to C2 into root of P by EI. Okay. So either C2 must be equal to 0 or root of P by EI must be equal to 0. So root of P by EI cannot be equal to 0 because without load, without the material, without the cross section, load cannot be applied, but C2 can be equal to 0. So substitute that in the deflection equation, the value of C1 and C2, you get this. So at the end, at the B end, other end of the column, x is equal to L, y is 0. Substitute the value of x and y in this expression. So m0 by p, m0 by p on either side will get cancel each other. You will get 1. So cos of L root of p by EI is equal to 1. So cos 0 is 1. Okay. Cos 360 is 1. So let us take the least practical values. So taking the least practical value, L into root of p by EI is equal to 2 pi. Squaring on either side, you get P critical or P crippling load is equal to 4 pi square EI by L square. So this is the Euler's critical load formula when both the ends of the column are fixed. When both the ends of the column are fixed. Now let us determine the critical load formula, Euler's load formula, when one end is fixed, other end is hinged or pinned, hinged or pinned. Okay. So the figure shows where the one end is fixed, the other end is pinned or hinged. Okay. So here at the top end it is pinned. Okay. At the bottom end you can see here, since it's a fixed end, m0 moment will also act. At the hinged end, an horizontal force H is acting, so that the force, the horizontal force H is restrained by this moment m0 at the bottom. So if you take a moment here with respect to this point, H into this distance L minus X clockwise positive, and this P into Y gives you the negative bending moment. And equate this to EI d square y by dx square. So divide throughout by EI, and after rearranging it, we get this equation, differential equation d square y by dx square plus p by EI into y is equal to h by EI into L minus X. So the general solution, you just multiply the right hand side by EI by p, you will get h by p into L minus X, which we have to add with the general solution, which we get for when the right hand side term is 0. That is y is equal to C1 cos of x root of p by EI plus C2 into sine of x into root of p by EI plus h by p into L by x. Okay, these first two terms, C1 and C2, will come into picture whenever you get the right hand side term to be 0. Okay. Whenever you get any right hand side term, you multiply it by EI by P and add with the existing general solution. Now this is the solution. And since you have fixed end, you differentiate with respect to x, arrive the slope equation. So at the fixed end, x is 0, y is 0, and slope is also 0. At the hinged end, x is equal to L, deflection alone 0. Okay, slope is not 0 because it's a hinged end or pinned end. So x is equal to 0, y is equal to 0. Substitute in this, you will get C1 is equal to minus h by p into L, and x is equal to 0. Slope is also 0. You get C2 to be h by p into root of E by p. Now substitute C1 and C2 in the deflection equation. At the hinged end, x is equal to L, y is 0. Okay, substitute here in this, you get this term. So you have got sine term and cos term, and h by p everywhere. It will get cancel each other. Sine of L root of p by EI and cos of L root of p by EI. Sine by cos will become tan, sorry. So tan of L root of P by EI is equal to L into root of P by EI. So tan of some angle, it should be equal to some value, which is in radian. So let us take that L into root of P by EI is equal to 4.5 radians. If you just convert that to degree, and if you take tan of that, you will get this value on the right hand side in radians. So squaring on right hand side, squaring on both the sides, you get P is equal to 20.25 EI by L square. So this 20.25 can be written in terms of a pi, which can be approximated to 2 pi square. So we write the pi square, P critical load formula as 2 pi square EI by L square formula when one end is fixed, other end is hinged. So now we have seen the derivation for Euler's load formula, critical load or crippling load formula for all 4 end conditions. Let us say when both the ends are hinged, P critical will be pi square EI by L square. When both the ends are fixed, critical load formula is 4 pi square EI by L square. When it is fixed, one end is fixed and other end is free, the formula is pi square EI by L square. That is a 4L square. When one end is fixed and the other end is hinged, the critical load formula is 2 pi square EI by L square. Okay, where L is the original length, E is the Young's modulus, I is the area moment of inertia. And here the value of I is very, very important. For example, if you take a rectangle section, let us, the formula is IXX. Let us take the formula IXX to be BDQ by 12 and IYY to be DBQ by 12. If you calculate IXX and IYY value, which value we have to plug in to the formula in place of I is very important. So when you calculate the IXX and IYY, check which one is the minimum value or least value. That value we have to substitute in place of I, in place of Y. Always you remember this I is nothing but the minimum value of IXX and IYY. You have to check which one is minimum. That value you have to substitute. Okay, if you take a circular, it doesn't matter because IXX is equal to IYY is equal to pi d power 4 by 64. Whether it's a solid circular column or hollow circular column. If you take different sections like I section, column or other sections where you get different formula or different values for IXX and IYY, you have to choose only the minimum value. You have to choose only the minimum value. That's very, very important.